scholars, a quick one here, continuing with Unit 5, Simple Harmonic Motion. We're going to talk about first periodic motion and then what makes periodic motion simple harmonic. The two classic examples that we're going to deal with of simple harmonic motion are our spring mass system, which looks like this. Oops, start that over. See, it's going up and down, up and up, up and down. And the simple pendulum, left and right, left and right, left and right. Now, periodic motion is just any kind of repetitive motion, and I've already written out a few notes, so feel free to pause and write this down. Periodic motion has three key variables that we can measure. The first is the period of time that it takes to repeat one cycle. We call that simply the period t, measured in seconds. So for example, maybe that pendulum takes 1.3 seconds to complete one back and forth. That would be considered its period. Now, the frequency, that's a number that, or a term you've likely heard before. The frequency is just how many times the thing happens every second. As an example, I have here a frequency generator that's going to play a 440 hertz. That's how we measure frequency sound. So listen real quick, or listen for a moment. Okay, that kind of annoying sound. I'll show you what the screen looks like that I'm looking at. It looks like this. So I'm setting the frequency at 440. You can see that the type of wave that it's making, the speaker on my phone, it's actually making what looks like a sinusoidal wave. If you've not seen a wave like that before, we're going to discuss it a little bit more. You'll notice that from one peak to the next, that is labeled T for period, and then 1 over that is the frequency, 440 hertz. If you're a music person, by the way, that is an A note, A440, a classic. And then finally, for periodic motion, that's just any kind of repetitive motion, that's the amplitude. So that's the maximum displacement from equilibrium. So as an example, if we pull back down our video of our friend the pendulum, these are angle degree marks. So you'll notice it goes about 10 degrees, or it looks like, oops, try that again. So from the middle there, it looks like it goes about, oh, I don't know, 10 or so centimeters, maybe 15 centimeters. So that would be considered its amplitude. We measure amplitude A in meters. If you haven't yet, take a moment, pause, and write all that down. So that's when we get to simple harmonic motion. Simple harmonic motion is periodic, repetitive motion that has a restoring force that's proportional to the displacement, meaning that the period, frequency, and amplitude are all constant. So you could, of course, have something like a saloon door, if you've ever seen in like the movies, that goes and eventually stops moving. That would not be considered simple harmonic motion. But if you have a pendulum or a spring that bounces up and down, keeping consistent period, frequency, and amplitude indefinitely, that's considered simple harmonic motion. Now the reason we're tying this in with Hooke's law is because you can see here that proportional to displacement thing. Now we're not going to go over all the details, but Hooke's law, we'll just put the magnitude there. This is, remember, Hooke's law. Hooke's law actually forces a spring, when it's well behaved, to undergo simple harmonic motion. And for reasons that we're not going to get into, you can do some math. When you keep a pendulum's swings small only, small pendulum swings only, then you have simple harmonic motion. I forgot to mention this, but often we'll shorten that to SHM for simple harmonic motion. All right, so the last thing that we're going to mention is the two formulas on your equation sheet about simple harmonic motion. Now, I think these are going to look a little bit intimidating at first for various reasons, and we're not going to go through the trouble of proving these, though they can be proved. If you are curious about that, I am going to post some resources on Google Classroom about where these equations come from. But what we want to be able to do in physics is make predictions about simple systems, and we're keeping the systems simple by constraining things to things that only obey Hooke's law, or pendulums that are swinging a small distance from equilibrium, something like less than 10 degrees. So anyway, without further ado, let me show you the period of a spring mass system. I'll cover up the pendulum for now. So this is the period T of a spring, and it's equal to 2 times the constant pi. That's right, somehow circles are related. If you've learned about the unit circle, you might have some idea where that comes from. And then take the 2 pi, multiply it by square root k over m. K here being the stiffness of the spring, and the mass being how much mass is hanging off of your spring mass system. You can also have sideways spring mass systems, which we'll see. Now, the period of a simple pendulum is actually pretty similar. What you'll notice is that it's still the period, which we write t with the lowercase p here for pendulum. 2 pi times the square root of L over G. Here, L is the length of the pendulum, and G is the acceleration due to gravity on whatever planet you're on. So what's interesting is that on Earth, the only thing that you can do, I don't know how well you're going to be able to see this, the only thing you can do to change a pendulum, so like these are my keys swinging, the only thing you can do to change the period, right now it's taking a little bit of time, is to shorten how long that pendulum is. So notice when I swing it now and let it go, it's swinging much more quickly than it was when I went the full length. So kind of surprisingly, the only factor that impacts the period of a simple pendulum is its length. On the other hand, when we talk about a spring mass system, the two things that affect its period are the spring constant, how stiff the spring is, and the mass. The last thing I want you to do is see if you can show what the frequency equation would be for both of these. Your hint is that frequency is defined as 1 over the period. So I'm going to ask you to pause. I'm going to write out the answer and not show you the algebra. See if you can get the same thing. Good luck. There you have it. All I did was flip everything. There is the frequency of a spring mass system. There is the frequency of a simple pendulum. We're going to talk a lot more about these. Here is how you actually do that. Because you've got your, I should put the pendulum equation. Because you've got your spring and pendulum equations, it's just a matter of writing it all 1 over. So 1 over the period, 1 over this whole mess. The 1 over 2 pi, you can't really do anything, and then you just flip the root k over m. Same with the pendulum. So we're going to do a lot more with this. Thank you, scholars. Have a fantastic rest of your day.